right. Well, hello everyone and welcome. Um, my name is Luis. I work in AI for material discovery, and I'll be hosting these weekly webinars under the AI for Chemistry Materials work group under the AI Alliance. And just a few words on the AI Alliance. So it's this community for open science and open research. We are 150 members organization, so 150 plus, sorry. So there's like industry, academia, um, government stuff, and so on. And the idea is to like work together, collaborate, and release open source AI. There are 6 different focus areas, and for this specific webinar, we are in FA5, so focus area 5, foundation models and data. And within this focus area, we have the AI for chemistry and materials work group. So yeah, thank you, the AI Alliance, for hosting this. And today we have Eduardo. He's going to be presenting actually a model under the AI Alliance that was released open source. So if you have any questions, please write them in the chat and I'll read them out loud or wait until the end, depends. And the meeting will be recorded and we'll post it on YouTube yeah, when we get a chance. So Eduardo, I think all yours. I'll let you present.
Okay, thank you very much, guys. Can you see my screen?
Yes, now yes.
Okay, so thank you very much, everyone, for joining. Today I'll be presenting our SMI-TED, which is an open source foundation model for chemical modeling. This model is open source through AI Alliance. It's from IBM. And this is a joint work from me and my colleagues, Emílio Vital Brasil, Victor Chirasuna, Renato Cerqueira, Dimitri Zubarev, and Kristen Schmidt. But before I start, I'd like to define what is foundation model for us. In our mind, in our concept, we see foundation model as any model that is pre-trained on a broad data or a very large data sets, generally using self-supervision at scale. I'll be explaining what is this in the next slide, which can be adapted or fine-tuned to a wide range of downstream tasks. So by now, what we're doing is we can build a very large model and we can specialize this model easily to different downstream tasks, to different tasks that we need. So this is very different from what we have seen during the machine learning or the machine learning era, for example. During the machine learning era, what we had is learning algorithms that we tried to teach them how to specialize for some tasks. So we need to specify all the data, all the features that we used. And then we had this deep learning area where we created some architectures that we were able to autonomously extract features or extract some specific characteristics from the inputs, from the data that we had. And now with foundation models, what we create is very big models, which these models can have different functionalities. So these functionalities emerge from this single model. And this was able mainly because of this revolution that the transformers brought to the machine learning or to AI. The first specific revolution is about self-supervised. So while in, for example, machine learning or deep learning, we needed labeled data, so we need to have labels to train, to create our models. With the self-supervised learning or the data learning from itself, we didn't need these labels, which is very expensive. So we can train the data based on the data, and it's possible through this self-attention mechanism. that help these transformers architectures to learn from their interaction with the data. Another thing is that this transformer is highly parallelizable, so we can parallelize this very easily. And this allows us to train in scale. So we can train this with the hundred thousands of GPUs at the same time. So all of this provide us this scale that is needed to create such large models. And based on these concepts, we at IBM came with this initiative, which is a foundation model for materials. But it's not only foundation model for materials, it's open source foundation model for materials. We believe in open source. We believe that with open source, we can improve the area, we can bring these new innovations to the area. And the idea of this open source foundation model is to create different foundation models, so different unimodal models for different representations that we can put all together in a meaningful multimodal way. So we are working with different representations, 3D atom positions, graph serialized, which is smiles, selfies. So we can tokenize this and bring this to a unified embedding space or latent space. So we now have 3 different big groups in our foundation model initiative. The first one is based on graph serialized, which comprehends smiles, selfies, graphs. We have another one based on DFT 3D electron density grids, and another one based on 3D atom positions. And the idea is to create a multimodal embedding space which we can adapt for different downstream tasks. This includes classification, regression, but also similarity. We can do similarity between these different modalities, indexing, so we can do retrieval. So for example, from a very cheap representation as a smile, we can retrieve very expensive representations as DFT3 electron density grids. For sure, it has some limitations that we are exploring, but the idea is to create this multimodal embedding space, multimodal space that we can navigate through the different modalities. So, for example, we can go from smiles to these different representations that we have, or from 3D atom positions to these different representations. So here we try to illustrate all this idea. And the first model that we brought to this, and it's a completely open source model, so which means that we have code, we have weights, we have all the resources necessary to reconstruct this model available. It's the SMI-TED. So the SMI-TED, it's a transformer-based encoder-decoder model. It is encoder-decoder because of this idea that we have to encode in a latent space and decode after. But during the presentation, I will also show how this encoder-decoder helps the model to be better. So this model was constructed using 91 millions of samples of smiles, which we curated from PubChem. By curation, we mean that we deduplicated the data, we removed all invalid molecules, and we canonized this data. So we have made sure that we have 1 smile per molecule. And this generated for us an amount of more or less 4 billion of molecular tokens, of pieces of these smiles to train our transformer model. We have this model in 3 different versions. So we have the base version, which is 289 million parameters. We have a mixture of experts. We have eight experts working together. And we have also available a Mamba version of this model. We pre-trained this model for 40 epochs using 24 V100 GPUs. This model has two modules, as I said, the encoder and decoder. The first part, the encoder part, is trying to learn based on a masking approach. So we mask the tokens, and the model tries to understand or tries to learn based on this masking. And the decoder part is trying to reconstruct the whole smile. So it's trying to reorganize the latent space to reconstruct, to give us back the smile. And during this process, we created this latent space that we can use to different purposes. For example, for these downstream tasks as molecular properties prediction. And this molecular properties prediction was the first benchmark that we used to evaluate our approach. So we compared our SMI-TED against the state of the art using this common approach in machine learning, which is this benchmark. Here we compared using the molecule net, so we have different tasks from different natures. For example, we have QM9, which evaluates the quantum mechanics of the molecules. We have 12 tasks there. And we could observe that our model performed very great in these benchmarks. We could, in many cases, surpass the state of the art. But this is just benchmark. This is just to illustrate or to observe how this model that we're generating works. Yeah, and when we mixture the models, when we have this combination of the models, we have better performance. We could observe this. And based on these benchmarks that we have that showed us that this model is able to do this prediction, it's generating a good latent space. We build different, we tried to perform different experiments to evaluate in a more rigorous way our approach. So as I said, this SMI-TED is open source. Everyone can go there and download it and use it. And then the second step that we want to use the model was for reaction yield prediction. And for reaction, what changed? The reaction smile is different from common smile. So based on this model that we have, based on this, we had to extend the vocabulary very easily. So that's the idea of the foundation model. We still having the same model. We just need a few adaptations, so an extension in the vocabulary to accommodate this type of smile. So a reaction smile has the reactants and the product separated by an arrow. It forms a big smiles with these different tokens that we could use to extend the vocabulary that we were generating. And for reaction smile, so we didn't, so this is the first time that the model is seeing this reaction smile. And we did this fine tuning for this type of representation. And we could observe that the model performed very well for this case when we compared it to the state of the art, which is mainly based on some common approaches. We have a bird there, but we could also surpass this bird. But the thing that really surprised us, it was about this specific result. So we did just 2.5% of the data for training and the 97% for testing. We still had a very good result in terms of classification of this reaction yield prediction task, for this reaction yield prediction task. So what this result shows for us, that because we did this massively pre-training before, because the model has this knowledge inside, we needed very few adaptation. So in this case, just 2% of the training data to still having very good results. So the model has this beforehand knowledge, and this make it easier for us to make this adaptation. While this the other models that we compared, they were constructed specifically for these tasks. They needed more training data to build their knowledge. Because we have this foundation model approach, we have this foundation model vision of the things, we had this very few adaptation for this task. And this is very impressive. And then we tried to understand, what is the latent space that we're generation? What this latent space can tell for us? How can we interpret it? And then comes the decoder part, which makes this history more interesting. So to evaluate or to understand the latent space, we performed one study that we constructed 6 families of carbon chains, as we have here. And for each of these family, we tried to generate a sequence of carbons in the end of the string. And we tried to observe how this model that we're generating, how this foundation model, which is based on encoder-decoder, compares to a foundation model that it's only encoder, that does not learn this organization or this SMILE reconstruction. And based on this, we could observe, for example, that malformer, which is which is an encoder-only model, which learns just based on this masking process, makes a latent space that it's not well organized as our model, that it's based on this encoder-decoder. So we do masking, but we also do SMILE reconstruction. We also try to bring some semantic to our model. And this made the latent space much more organized. So we can see here clearly, when we add these carbon atoms to the end of the strings, how our latent space behaves. We can see this sequence. And this sequence allowed us to perform some few-shot learning assessment. So based on this, we can do a sum in the latent space. So without any adaptation, just summing embeddings, and we could reconstruct a SMILE with an emote similarity of 92%. So we could reconstruct a SMILE based on this summation with a very high similarity without any fine-tuning. And this is very interesting. So we could observe that actually this decoder part helping this organization, helping in create a more organized latent space. So we tried to bring this type of example to another study, trying to understand if the model is able to do this relationship about the molecular structure plus properties. If the model is able to learn this relationship. So in this experiment, what we did, we have the QM9 data set, which has these different tasks, and one of the tasks is about HOMO energy. And it's known that the HOMO energy is influenced by nitrogen. When the nitrogen is included in the molecule, we tend to have high HOMO energy. So, for example, in the whole QM9 data set, we know that 90% of the molecules has nitrogen. But when we look to the top 10% of the molecules by HOMO energy, 32% of this molecule has nitrogen, which indicate this for us. And when we observe this in the latent space, when we put this in the latent space, we filter the top 10% HOMO energy, and we try to observe the molecules there. We can see that, for example, an encoder-only model, like Morphomer, cannot separate the things. We can see that the nitrogen and the non-nitrogen molecules are all mixed in this latent space, in this data space. In our case, which we have this decoder, it helps to semantically organize the things, semantically put all the things together. So we can see a cluster here of nitrogen with the high HOMO energy without any fine tuning. Just the model as it is, it helps to do this organization of these molecules together in the latent space. And we could evaluate this using some clustering metrics that will really show us that the SMI-TED is able by itself to do this organization, to do this clustering, putting together nitrogen and molecules with a high HOMO energy. And this could help some interpretation or some analysis, some deeper analysis of the latent space that we are generating. So based on these conceptual tasks, we now went to the lab and tried to understand our model in real scenarios using real data. So we have two use cases that I'll bring here. The first one is using the SMI-TED for the classification of surfactants phase diagrams. So the SMI-TED trying to reconstruct these surfactants phase diagrams. So we have 90 different phases for each surfactants, and this model was adapted for this prediction. So we have as input from our model the surfactants, which is encoded by this SMI-TED, and we also have some extra features which we can concatenate in the latent space, which is about the compositions of the surfactants and the temperature. So basically we are constructing a feature vector which has 768 features coming from the encoder of the SMI-TED. So we transform these surfactants in this feature vector, and then we concatenate it with these external features, which is composition and temperature, and we can send this to a learning algorithm, in this case a fully connected layer. And we could observe that just in this case, in this specific case, we have 8 complete diagrams for training of the models and 4 diagrams for testing. So it's a very limited data, but we could observe that the model is capable to predict this phase. For sure, we have some difficulties on these transition phases. We can clearly observe here that the model tends to fail in this transition phase, phases. But we are now extending our model with some uncertainty analysis to try to capture better this transition phase. But in the major of the phases, we could correctly capture. We could correctly understanding how these phases change along the different compositions and the temperatures. And as I said, we trained this with very limited data, with just 80 surfactants phase diagrams for training. And we tested this with 4 phase diagrams. But this is interesting because this data was made in lab. So we can also go to lab and produce more data or try to predict or screen with our model and then check in lab. And that's what we did for this next use case that I will show. In this use case, we used the SMI-TED, our foundation model, to design high ionic conductivity electrolyte formulations. So the idea here was to have big formulations where we concatenate the chemical compositions, the chemicals plus the compositions using a special token or a separation token, so we can make the formulations as a very big string, which we can input in our model and use to fine-tune this model for this new type of representation. For sure, we can also have some extra features. In this case, we have a temperature as this extra feature, and then we can predict this ionic conductivity. So basically, we have this new representation, which is a formulation, and all these elements that composes the formulation we have in our vocabulary. So we don't need to, in this case, to update the vocabulary. We just need to update or the way that we build this representation. The model is able to encode this. We can fine-tune upon this. And we can also include some extra features to improve our model understanding about the problem. And then we can predict this ionic conductivity. So in this case, we had a training data set of 13K training points, and we tested it in this benchmark data set, and we could observe that the model works very well. We had a high R-squared with 0.97, a low RMC score, and that's great. But we wanted to validate this in lab. So what we want is not only to have these nice results in unknown data. We want to make this really valid in lab, to really understand how our model can work, how it can really accelerate these discovery things. So we build a data set of 100,000 formulation combinations. So we have the 6 chemicals and the 6 possible combinations. And we wanted the model to screen this to predict the ionic conductivity for this 100,000. And from this very big group, we could identify 16 candidates with a certain threshold, in this case 10. So we could identify these 16 candidates, and then we went to the lab to validate this, to really understand if the model could capture or not, if this makes a valid formulation or not. And during this experiment in lab, we found that 7 out of these 16 cases was really valid. So here I have the table with the formulations that we discovered. So a success rate of 44%. In typical experiments like this, the success rate is 10%, which means that our model really accelerated or helped this discovery process and validated in lab. And when we look to the data set that we have, we discovered the electrolytes formulations that were not, that never happened in the training data set. So values, high ionic values that never happened in the literature data set. So we could go out of distribution, or we could extrapolate the models, or extrapolate the SMI-TED for predictions that it never was seen during the training. The model was able to extrapolate just based on this knowledge that it has about these compositions or these formulations. So here we have the table with all these formulations that we discovered and validated in lab. We have a preprint for this study. It's here, and we are now trying this on more different real use cases to really validate the usefulness of the model. As I said in the beginning, everything that we are doing, everything that we believe is now open source. So it means that all the training code, not only training code, but training code on these multiple GPUs, fine-tuning scripts, evaluation scripts, weights, everything is open source. Everyone can go there, check our models, test our models, can send a message for us if the model needs any adaptation or any help that it's needed. And this is part of the alliance. So this is part of this great group that really believe in this open source, really believe that open source can change everything. Yeah. Sorry, just one last slide. So as I said, everything is open source. Another thing is that we also want to understand this interaction about human and AI. So how can we construct models that are really useful for the experts? So we don't want just to build models. We want to build models that are really useful, that it's really attend to the needs of the experts. So here, if you wanted to participate in this research, please, you can contact Dr. Siakande or Dr. Emilio, and join this really interesting research. I'll quickly show also, this is our collection in the Hugging Face spaces. So there we have the different models that I talked. We have the atom position models that we just released at the ACS Spring. We have a model for graphs. We have the model for selfies, which is really very interesting. We have the Mamba version of our model, and we have the SMI-TED. So for SMI-TED, you can see we have all the files there, the vocabulary, the model weights, everything is included there. And if you have any question, you can contact me or you can contact Emilio. Here is the GitHub with all the source code, all the things that are necessary to reproduce or to extend this work that we're doing. It is all open source, and if you have any questions, you can also contact all the authors of this repository. And I'm really thankful for this opportunity to talk for this audience, if you have any question, I'll be really happy to answer all of them. And thanks.
Thank you so much, Eduardo.
Thank you.
Yeah, if you guys have any questions, please write in the chat. I have a few questions while we wait
For
for more questions. So you said that the model has 289 million parameters, right?
Exactly, the base model.
Is that encoder-decoder or only encoder?
The encoder-decoder, the whole model, so the two pieces of the model, the two modules has these total parameters.
And
The decoder, if I'm not wrong, it's 100 or almost to 200 million parameters. It's larger. But
okay.
this decoder part, which is important for us to do this organization or to bring this semantic to the model.
Yeah, about that, you mentioned that in the nitrogen slide, right?
Yes, yes.
Could you show it back again, please?
Yeah,
And
yeah, for sure.
maybe explain your understanding why the decoder could help.
Here, yeah.
Yes, that's one. So, what is your intuition to say that the decoder could help separate this space versus like an encoder only model?
Yeah. When we use or when we train this decoder, what we're trying to do is to reconstruct the whole smile. So basically, we're trying to make a latent space that it's organizing by some semantics or some tokens. We're trying to reorganize the tokens together. We're trying to put some semantics in the model. And we could observe this during this experiment. We could observe that these nitrogen molecules, they tend to group together in a space, in this latent space, which the encoder model, which the encoder only model, it's not able to do, because the encoder just learned the masking, just learned to mask, but it doesn't learn this full representation back. And that's the main difference for me, at least. It's for sure it's some hypothesis of semantic learning. Yeah.
Okay, okay, that makes sense. And did you try to do the same thing for other functional groups?
Yes, yes. We are trying to do this for a carbon group with the other properties, and it seems to work in the same way. We still finalize the experiments, but we could observe this, and we are also training a contrastive learning approach, which tries to mix these different modalities. And we could observe in this multimodal latent space that we're generating, that when we use this decoder model to learn this mutual representation, the decoder helps in this alignment, helps in putting all these things together in a semantic way. For sure, this is a thing that we are trying to experiment. It will be available soon, but we could observe this in some internal experiments that we are doing as well.
Thank you. There is a question in the chat.
For
Can you
sure.
please talk about the downstream tasks you've seen with this model?
Okay. Yeah, we use this model for different downstream tasks. So we tested in these benchmarks, but in terms of real use case, we have three different projects that we are working. The first one is this surfactant phase diagrams, which we are evolving this work with the 2D data, two-dimensional data for a three-dimensional surfactants phase. And the idea is to have the same type of accuracy for this data. we have this model for this battery project that we have, that we want to improve the the performance of these batteries based on different properties. And for this ionic conductivity was very interesting in this case, because we could really validate this in lab. We could really generate new formulations based on this screening of the model, constructed by the model. And the third one that I didn't show is about PFAS, where we want to classify, we want to identify some PFAS molecules, and we want to evaluate the toxicity of them and the different properties, and bring in new. Hello?
No, all good, all good.
Okay, okay. So the idea is to replace this PFAS with some form of analogous molecules. Yeah.
And I can add one comment. I actually also use the model, the SMI-TED for the toxicology 24 challenge, which was just like small molecules and predict toxicity. And yeah, it worked great.
Oh,
And
nice,
get
nice
first
to hear
place,
about
but it
that.
worked.
Yeah, yeah, and that's the good thing about the open source. The idea is to bring this to the community and observe the model working in different downstream tasks, in different approaches. And I'm really happy to hear about this, that it would work great. Did you fine tune the model or just use the model as?
Yeah, full fine tune.
Oh, great. Did you use our script for fine tuning?
No, I actually went into the code and like did it like myself.
Okay, okay.
Yeah, yeah.
Perfect. But if you
There,
need any
yeah.
help, anything, you just let me know.
Thank you. There's another question. They're asking on the possible extension to polymers, which I think you
Oh,
have to say.
yes, yes, that's a good question. And actually, we have a version of this model for polymers. So we extended the the vocabulary that we have with a P-Smiles vocabulary. And the model worked really nice. We have a paper on this. We published that the AI for materials in the last NeurIPS. Unfortunately, this model for polymers will not be open sourced, at least by now. But we have an extension of this for polymers. Yes, thank you for the link, Luis.
No worries. Um, I have another question since there are no more.
Okay.
um, so this model pretty much is an autoencoder, right? Encoder decoder.
Yes.
Did you test like did you test it as an autoencoder? So for example, I was looking into like latent diffusion, and for latent diffusion, you need like some embedding space, and then you have diffusion and some embedding space at the end. So you need some autoencoder.
Yeah.
Did you try using it for something like that?
Yes, yes, we are trying this now, using this latent space that we're generation as a condition for a generation of some grids, or these 3D grids. We're still struggling with this because of some geometrics. It's about equivariance problem, but we could observe that this helps the model to bring some semantic in the end. It's a good research question that you have, and so there are things to explore in this direction.
Okay. And do you have in the pipeline of work that you have, like, do you have like the 2D or 3D version of this autoencoder?
Yes, we have, and we plan to bring this open source at least by the mid of the year, so by June, July.
Okay, that's
So
great. I'll look forward to it. Um, yeah, I think there are no more questions, so I guess we can close it. And thank you so much, Eduardo, for your
I'm
time.
really thankful for the opportunity. Thank you, everyone. If you have any questions using the model about anything, please contact me. I'll be really happy in answer all of them.
Thank you. And thank everyone for joining. We'll be uploading the recording to YouTube, and we'll be having these webinars every week. So Yeah, thank you, everyone.